this is section 7 for our course, and we're going to do the prep skills, which the first skill is to reduce fractions. With the prep skills, remember, a lot of these are things that you've probably seen before, but may not have done for a while, so just skills that you'll need in the class that are good to review. So in this case, lowest terms, when you're dealing with fractions, lowest terms or reduced means the same thing. And of course, any two numbers will have a common factor of 1. But in order for a fraction to be reduced to lowest terms, we need that the numerator and the denominator don't have any other common factors. So no other factors, nothing that can divide into them besides 1 that they have in common. So for instance, 4/6 is not in lowest terms because you can divide 4 and 6 by 2. So you're looking for anything that will divide into both of them. Now in this case, you have a 6, but you have a 25. So there's nothing that will factor into or divide into 6 and 25 that they share in common. For instance, the only things that will divide into 6 are 1, 2, 3, and 6. 1 times 6 is 6, and 2 times 3 is 6. Those are the only things that will divide into 6. The only factors of 25 are 1 times 25, and then 5 times 5 is another factor. 5 divides in 5 times, and then the 25 with the 1. So they have several factors, but they don't share any factors. So the process of writing fractions in lowest terms is called reducing the fraction. And when we do that, we're trying to make it so that we can interpret them and look at them in lowest forms, because otherwise we may not recognize that two fractions are equal to each other if one's written in an unreduced form and one's written in a reduced form. So for example, it says it's a lot easier to see that 5 halves is 2 1/2 than to see that 180 over 72 is 2 1/2. Those are equivalent fractions. They are the same fraction, just 180 over 72 is not reduced. But that's pretty hard to tell by just looking at them in their different forms. So for this first one that we looked at, let me roll this up a little bit, the 4/6 that we talked about, since it's 4 and 6 are both divisible by 2, we're going to take the top and the bottom and divide both of them by 2. As long as we divide the top and the bottom by the same thing, we'll end up with an equivalent fraction. And if we continue that process of dividing out anything that they both have in common until they don't have anything else in common, then we have it in reduced form. So 4 divided by 2 is 2, 6 divided by 2 is 3, and that's in reduced form. 30 over 12, 30 divided by 6, and 12 divided by 6, they both are divisible by 6, so we do that, and it reduces to 5 halves. Now, don't get too worked up on finding the greatest common factor. They're always, in the books, get real hung up on the greatest common factor. Say you were looking at 30 and 12, and you didn't think about 6. Say you only thought about the 2 or the 3. Let's go with the 3. So let's say you only saw that they were both divisible by 3. And so you went divide by 3, and you got 10 over 4. Well, hopefully at that point, then you just take another look at that and you say, oh, wait a minute. But 10 and 4 are also divisible by 2, so I better reduce again. So it's okay to take a couple steps to reduce. In fact, I would recommend it because it's usually faster to just do a couple steps than it is to hunt around for that greatest common factor so that you can just divide once. The divisions don't take very long, so just kind of grab the first thing you think of, but after you do a step, make sure that you look at what's left, like in this case the 10/4, and make sure there's nothing else that can be divided out of it. So that's reducing fractions. Our second skill is converting between fractions, decimals, and percents. So we already know, we've talked about how we could take 3/5 and turn it into 0.6 by taking 3 divided by 5 on your calculator. And if the fraction does not terminate, we can round it, and if you do round, it's really good to put these little squiggly lines to show that it wasn't exactly equal to 0.43, but it was close to it. So the squiggly lines mean approximately. So in this case, when you divide 3 divided by 7, 3 divided by 7 comes out to be, on my calculator, if I just write out all the digits, which I wouldn't want you to do, but just so we can talk about it, I get 428,571,429. Now, I don't even know if that continues further because that's just all the spots my calculator has on the screen in order to display. But if we say, well, we don't need all of this, we just need an approximation, say I decide to go to that second decimal, I still have to look to that third decimal to decide, do I leave it 0.42 and just cut it off, or do I have to round that 4.2 up to a 4.3? Well, in this case, because that's an 8, we decide we're going to round to 0.43. And then if we have a decimal and we want to switch it to percent, we're always going to shift the decimal to the right two places. So we're always going to shift that to the right two places, and from decimal to percent, and that becomes 43.5%. In essence, what we're saying is this is the 10th spot, this is the 100th spot. So if we take something just to the 100th spot, say we have 0.27, this literally means 27 hundredths. And 27 hundredths is the same as, you could write it this way, and then 27 hundredths is the same as 27%, because percent means per 100. And so you can see these are all equivalent, and all we've done to get from here to here, in essence, is just taken and shifted that decimal to the right twice. So some people like to think of it as multiplying by 100. Some people like to think of it as shifting it two places to the right. But whichever way you do it, you still get the same answer. So in this case, if we write this percent in decimal form, this time we're going backwards. So instead of, we're already in decimal form, we're trying to go back to, we're already in percent form and we're trying to get back to decimal form. We're going to shift it 2 spots to the left. And so 8.2% is the same as 8.2 out of 100 is the same as 0.082, because this is just a little over 8 hundredths. 8 hundredths would be 0.08, and we have just a little bit more than that, 0.082. And then if you start with a percent and you want to write it as a fraction, you could start with the percent, then you can write that over 100. So 70% is literally the same thing as 71 hundredths. And then if we reduce that, 71 hundredths, I can divide the top by 10 and the bottom by 10, and I get 7 tenths. So 70% is the same as 71 hundredths is the same as 7 tenths. So here's our prep skills questions for Section 7. It asks to write these both in lowest terms, so we'll start with the 12/16. The first thing I see that goes into those is a 4. I think it's the biggest, but I'll double check what I've done. So 12 divided by 4 is 3. 16 divided by 4 is 4, and that's definitely reduced because there's nothing that 3 and 4 have in common. In fact, 3 is prime, so I definitely wouldn't be able to do anything to reduce that fraction down anymore. But 12/16 is better written in reduced form of 3/4 in most situations. 65/80, the first thing I see is a 5 in here, because anything that ends in a 5 or a 0 is going to be divisible by 5. So that gives us 13 on the top, and we know we're in reduced form because 13 is prime. And then 80 divided by 5 would be 16. So 13/16 is the same as 65/80 in reduced form. If you ever want to double check, you could, if you've made any sort of error or anything, you could always take the top number and divide it by the bottom number, see what you get, and then you could go back to your original fraction, 65 divided by 80, and see what you get. Compare the decimals that you get. If you get the same thing, then you know you've done it correctly. Like for instance, if I take 12 and divide it by 16, and if I take 3 and divide it by 4, since 12/16 and 3/4 are supposed to be equivalent, I should get the same thing every time, and you do. You get 0.75 both times. So we know that 3/4 is the correct equivalent equation, just in reduced form. For these with percentages, if we want to put them in decimal form, we're going to shift from percent to decimal. We're going to shift to the left, because what's in a decimal we shift to the right, but if it's in a percent going back to a decimal, then we're going to shift it to the left. So 60% would be 0.60, or you could just say 0.6. And then 12.5%, if I shift it 2 spots to the left, that's going to be 0.125. And then if I want to write each fraction in decimal and percent forms, 3/5, if I divide 3 divided by 5, I get 0.6. And we actually already had that up here, but we'll go through the process. So 0.6 is the decimal form. That's the same as 0.60, which is 60/100ths, which is 60%. You also don't have to necessarily do this. You can just shift this 2 to the right. We just have to add a 0 on the end. But 3/5 is the same as 0.6 is the same as 60%. And then 12/16, we're going to do, we already know from up here that's 3/4, but that doesn't really, well, we do know it's 0.75 because we already did it. So 12/16 is the same as 0.75. So that's decimal form. And then if I shift the decimal 2 to the right, that's 75%. So 12/16 is 0.75 or 75%. These two here, 0.13 is 13/100ths. So I could think of that as 13/100ths like this. And 13/100ths is the same as 13%. Or I could think of it as shifting it 2 to the right. And you get 13% that way too. Here, I think this one it's easier to just think of it as shifting, so we'll shift it 2 right, and you're going to get 5.8%. Write each of these percents in fractional form and reduce. So when we're talking about percent to fraction, we're just going to always write that over 100 because percent means per 100. Now we have 75/100ths. We're going to reduce that. If I divide 75 by 5 and 100 by 5, I get 15/20. And I did that intentionally because I wanted to show that, again, you don't have to get that biggest number. If you divide by 5 on both of those, then when you get to this step, you recognize, oh, wait, I still have a 5 that can divide out of both of those. So divide both of those by 5, and you get 3/4. Now, yes, we could have divided by 25 and done it just in one step, but if you don't see that right away, it doesn't really hurt if you just go with what you see first, but make sure what you end up with, like in this case, the 15/20ths, still doesn't have any common factors that you can divide out. So 15% is the same as 15/100. Again, I'm going to divide by 5, and that's going to give me 3/20. And that one is reduced, we know for certain, because it's got a prime number of 3. So nothing can divide out of into 3, and 3 doesn't divide into 20, so this has to be prime. So I'm going to pause at this point, and we're going to pick up with the video with lesson, it's called lesson 1/6 in the book that we're using, or in the book that we're borrowing from, but for our class, it's section 7.
In one, they tell you that the probability of rolling a 4 on a standard 6-sided die is 1 out of 6 because there are 6 possibilities and 4 is one of them. We're supposed to write that probability as a decimal and a percentage. So you need to go ahead and take 1 divided by 6 and rounding that to 3 decimal places, that comes out to 0.167. Now to convert that to a percentage, we'll go ahead and move the decimal 2 places to the right, and so that is 16.7%. So in number 2, in words, what does that say about the percent chance of rolling a 4? Well, that means that on any one roll, you have a 16.7% chance of rolling a 4. And what that also means is that on average, you would expect 4s to come up about 16.7% of the time. With that in mind then, in 3, if you rolled a die 300 times, how many times would you expect it to land on 4? Well, you would expect it to land on 4 about 1/6 of the time, or 16.7% of the time. So that would be 1/6 of 300. We'll do 1/6 times 300. You could also multiply it by 0.167. It just won't come out quite as nice because of the rounding. 1/6 times 300 comes out to 50. So we would expect it to land on a 4 50 times. In 4, though, how sure are you that you'd get exactly 50 4s? Well, I'm not really sure at all that it would come out as a 4 exactly 50 times. I'm just expecting it on average to be somewhere around 50 times. In 5, when a standard coin is flipped, how many different outcomes are possible in terms of which side lands face up? Well, there are two sides that could land face up, heads and tails. Those are the outcomes. So in 6 then, what is the percent chance that a coin lands on heads? Well, since there are two possibilities, that's a 50-50 chance of getting heads, so 50%. In 7, write the probability as a fraction. So probabilities as fractions would be just converting 50% to a fraction, which is one chance out of two possibilities. And then describe the likelihood verbally. Well, that means that each time you flip a coin, you have a 1/2 probability of it landing heads up, which also means that we expect on average for it to land heads up about 1 out of every 2 times. So then in 8, if you flipped a penny 80 times, about how many times would you expect it to land heads up? Well, you would expect it to land heads up about half the time. So 1/2 times 80 gives us 40 times. And then in 9, would you definitely get it landing heads up 40 times? Well, no. As we talked about before with the dice, we would expect it to, on average, come out close to 40, but not exactly. In number 10, they want you to look back at the probability diagram on page 75 for the poker hand that they had drawn there, and I've inserted a picture of it right here. And it contains a picture of a good hand in poker, 4 8s. If you were to randomly pick a card from that hand, what's the probability that it would be an 8? First, we're going to write it as a fraction. So out of 5 cards, 4 of them are 8s. So we would have a 4 out of 5, or 4/5 probability. They do ask us to use proper probability notation. So the probability of getting an 8 would be P parentheses 8, or P of 8, and that would equal 4/5, 4 out of 5. Now it also asks us to write that as a percent. So if you convert that to a decimal, it's 0.8, which is an 80% chance. Now in 11, it asks us to write a sentence describing the percent chance of drawing the king, not an 8. Well, for the kings, there's only one king out of 5 cards. So the percent chance would be 1 out of 5, which comes out to 20%. Writing that as a sentence, we have a 20% chance, if we draw one card from that hand, of choosing a king. Here you have to do a little bit of an experiment to get started. Tape a dime to a playing card and flip it a few times. And they suggest that any less than 20 would be a bad idea. I went ahead and did more than that to get better data. And so I flipped it 50 times, and it landed face up 33 of those times. So for this video, we'll use those values. In number 1, based on those results, what is the percent chance that the card will land face up? Well, I need to take the 33 times that it landed face up and divide it by the 50 total flips, and that gives me a 66% chance. In 2, write that percent chance as a probability between 0 and 1. What they're asking there is for you to write that as a decimal or a fraction. Let's go ahead and write it as a decimal. That would be 0.66. and then they want us to write a sentence about that. And that means that each time you flip that card, you have a 0.66 probability of it landing face up. Or we could say that on average we would expect it to land face up about 66% of the time. In 3, did you find the results surprising? Well, you shouldn't really find it surprising if you think about it, because by weighting one side of that card, you would expect it to pull that side down, leaving the card landing face up more often. And in number 4, perhaps the most important question here to think about is, why was empirical probability a better idea here than theoretical probability? Well, theoretical probability would have assumed that you had a 50-50 chance of the card landing face up or face down. Because we weighted the card, that's no longer true. But we don't have any theoretical information to figure out what the new probability would be. The only way we can figure it out is with an estimate using empirical probability. In 5, what's wrong with the logic in this conversation? I have a 50-50 chance of passing this exam. It's just like flipping a coin. There are 2 possibilities. I'll either pass or I won't. Well, the problem with this is it assumes that it's completely random whether you pass or fail an exam. And that's not the case. There are lots of factors that go into that, and there are many things you can do to make it more or less likely that you'll pass that exam. So in 6, what are some of the things you can do to change your probability of passing? Well, you can study more or less, attend class more or less, do more or less of your homework, spend more or less class time paying attention, and things like that. In 7, there are 45 applicants for 2 jobs, and you're one of them. If every applicant has an equal chance, what's the probability that you would get the job? Well, using proper notation, that would be P of getting the job. And if everyone has an equal chance, then that means out of those 45 applicants, they're going to choose 2 people. So everyone has a 2 out of 45 probability, or 2/45. We can also write that as 0.044. In 8, why is theoretical probability not actually very realistic here? Well, it's usually not completely random whether you get a job or not. Not everyone has an equal chance, and theoretical would assume that they did. It's far more likely that other factors come into play, and so an empirical probability for each person would make more sense. In 9, a program at a community college says that out of 480 graduates, 450 got jobs. So if you're a graduate in this program, what are your chances of getting a job? Well, in this case, it's an empirical probability. They're using an actual example of what happened. So your chances would be 450 out of 480. And so that comes out to 93.75%. That's a pretty good likelihood of getting a job. Here we're looking at the results of a study. 1,005 adults were asked how long it took them to know if they could stay in a new job long term. So in 10, what's the probability that a randomly selected worker knew within a week if she could stay in her job long term? So less than a week, that was 231 people out of the 1,005 that were surveyed. So 231 over 1,005, and that gives us a probability of about 0.23. In 11, what's the percent chance that a randomly chosen worker took more than a month? Well, more than a month would not be less than a week, not within a month. It would be any of the other 3 categories, half a year, within a year, or over a year. So I would need to add those 3 together. 241 plus 60 plus 71, and divide that by 1,005. And so that's 372 out of 1,005. And that comes out to about 37%. In 12, write a sentence or two explaining how likely you think it is that your professor decided if he or she could stay in a long-term job in a half year or less. So half year or less would be the half a year category or any of the shorter ones. So we have 3 to add together again. So that would be 231 plus 402 plus 241 over 1,005. That's going to be 874 over 1,005, which is about an 87% chance. So that means that your professor probably has about an 87% chance that they decided this within a half year or less. And in 13, they ask us to think a little bit about the validity of this survey. It was done online. How accurate do you think the probabilities computed based on this survey would be when trying to describe the feelings of all American workers? Well, you have to be very careful with online surveys. It is often particular groups of people who have access to the internet, the time to take the survey, and the willingness to take the survey. In question 1, according to the Census Bureau, about 51.5% of adults in America are women. So what's the probability that the next adult you run into is female? Well, 51.5% is the percent chance that that next person would be female. And so if we want to change that to a probability, we would change it to a decimal. So it'd be 0.515. Then it asks, what's the probability of that person being male? Well, to answer this question, we have to make an assumption that if a person is not female, then they must be male. This does leave out some cases, but the percentage is probably small enough to not throw the statistics off too much. So males then, if we make that assumption, would be the remaining percentage. So 100% minus 51.5% would leave us 48.5%, which is a probability of 0.485. So then in number 2, there are 535 members of the U.S. Congress. Based on the statistics from question 1, how many would you expect to be female? Well, if 51.5% of adults are female, then we would expect 51.5% of Congress to be female. So 535 times 0.515 comes out to about 276 women. In 3, though, they tell us that in reality there are only 104 women in Congress. So what does that say about politics in this country? Well, what it tells us is that proportionally speaking, women are underrepresented in Congress. In 4, you're playing a game. You get to roll one 6-sided die, and if you roll a number over 4, you win. So what's the probability of winning? Well, if you have to roll a number greater than 4, then that means 5 or 6 would make you win. So out of the 6 possibilities on the die, 2 of them are winners. So 2 out of 6 reduces to a 1/3 probability of winning. So then how good would you feel about your chances? Well, a 1/3 probability, that's a 33.3% chance. It's more likely that you won't win, but it's still a pretty significant chance. It's within the realm of possibility. In 5, you've got a math class. There are 30 students, 12 are of non-traditional age. So if you randomly pick one person from that class, what's the probability that you choose a person of non-traditional age? Well, if 12 out of the 30 are of non-traditional age, then 12/30ths, and we can reduce that. It reduces to 2/5, or if you wanted to write it as a decimal, 0.4. In 6, running an online simulator that collects information about habits in a class and predicts whether you will pass or fail predicts that this particular student will pass 7 out of the 10 times that the student runs the simulator. So how likely do you think it is that the student will pass? Well, the empirical probability based on the simulator is 7 out of 10, which tells me the student probably has about a 70% chance of passing. And in 7, what do you think is the probability that you will pass the math course that you're in? Well, you need to answer that for yourself, but is this a set value or can it change? Well, it can certainly change depending on how much of the semester you have left and whether or not you make any changes to your attendance or study habits.